Good afternoon again and welcome back. So we were discussing various concepts associated with the principal stresses as well as the maximum shear stress. So we'll continue that discussion and we'll also try in the process to solve one example. Okay. Before we can go on with those plans, you please note that we have obtained till now the answer for or the solution for theta p and the solution for theta s, and in each case we found out that there were two possibilities. Okay. Now let us quickly write them down again and see if we can obtain any connection that might possibly exist between them. Okay, connection between theta p and theta s. So let us quickly write down those expressions. So our tan 2 theta p was equal to 2xy, this, and tan 2 theta s was equal to minus of sigma xx minus sigma yy divided by twice xy. Now you see there is a certain pattern almost presenting itself to us directly. What happens if we just multiply these two things together? What do we obtain? This is equal to so tan 2 theta p multiplied by tan 2 theta s is equal to minus 1. Now you forget about all stresses, forget about all this circle and everything. Just take your mind back to your high school geometry. There, when we were considering the equations of lines and the various possibilities of slopes, we had seen that if the slope of one line is given by tan alpha and the slope of another line is given by tan beta, and it turns out that tan alpha times tan beta is equal to minus 1. So perhaps in the actual language of high school mathematics, high school coordinate geometry, it was presented to us in terms of m1 times m2 is equal to minus 1. So in that case what happens was that we can immediately conclude that those two lines are at right angles to each other. Now we have to remember one very subtle point here. You see, perhaps if you interpret that this twice theta p itself is like the alpha and this twice theta s is like the beta, then okay, this represents one straight line and this represents one straight line, and the angle between them this is pretty much evident to us, that angle between twice theta p and twice theta s should be equal to 90 degree. But that means that the angle between theta p and theta s should be equal to 45 degrees. Why is this very important? It is extremely important to note this because you see this theta p, it actually represents something physically, this theta s represents actually something physically. What was that? This theta p is the angle that the tilt of our little square element which we had been drawing here that makes with the horizontal axis, and this theta s correspondingly is the angle that square element makes with the horizontal. The difference was just that one of them pertained to principal stresses, the other pertained to to the maximum shear stresses. So what is the conclusion from here? Conclusion is that the plane on which we obtain the principal stresses and the plane on which we obtain the maximum shear stresses, they are tilted to each other by 45 degrees. It is not equal to 90 degrees. It is a major point of mistake that is made by many students. So I repeat that the angle that the plane on which the principal stresses appear and the angle on which the maximum shear stresses appear, the difference between those angles is 45 degrees. Okay. So, all of this abstract kind of theoretical discussion is fine, but can we perhaps connect this to a real life example, a very simple nice example that that all of us can immediately understand and get a feel for. So, what we can do is let us keep this thing at the bottom and let me borrow a little space from above. What I will do is I will consider a very slender rod. And then I will pull at both its ends. Okay. Now, what I will do is I will not focus my attention at this end and at this end, because I believe this has been covered in most of the sections, especially in the content that pertain to the previous tutorial sheet, that is tutorial sheet number 7, when we discussed about stresses and strains, was that this situation is like uniaxial tension. If we focus our attention very close to this thing, there is a certain distribution of stresses which is quite complicated to find out, but if we move a little bit away from that end, more or less in a very practical engineering sense, we can say that more or less a uniform state of normal stress will appear here. So, what we want to do is we want to single out a little element from here and we zoom into that. So, we are zooming into this little element. Now, here we are obtaining a certain value of the normal stress. So, the whole point of the discussion was that we want to remain away from the ends is that even if you consider this little element somewhere here, it really does not matter so much. Okay. So, we have this little square element where we have this normal stress. Now, on this surface we do not have any normal stress, here we do not have any normal stress. Now, I hope you do not mind if I erase this thing a little bit. Let me keep that theta p and theta s is 45 degrees. So, it is like this, that if I set up my coordinate axis in this fashion, x and y, then this one is nothing but sigma xx. Correspondingly, this is my sigma xx. It just so happens that my sigma yy for this particular example is equal to 0. So, can I not obtain my insights from whatever we have been discussing today and find out the angle between this one and this one? First of all, you tell me, if I have this kind of a situation where what should be the situation if I draw this kind of a circle? If we have this sigma xx, forget about sigma yy, you please note here there is no shear. I repeat, on this surface there is no shear. Correspondingly, I should not have any shear here also. Okay. If I do not have any shear there, then is it not true that I am actually sitting here? Because these are the points where there are no shears. So, the value of the normal stresses that I am obtaining just directly from this thought experiment or perhaps a real experiment is the value of the principal stress itself, the sigma xx. So, traditionally what is done is the principal stresses are traditionally represented by sigma 1 and sigma 2. Here I am noting that sigma 1 is nothing but my value of sigma xx, and that is nothing but the tension force divided by some area where this capital A represents the cross section of this very slender bar. So, this is my sigma 1. I have also said that sigma yy is equal to 0. So, what happens now? Where should my sigma 2 be? Well, why should this be true? Well, we have already seen earlier that the difference between the two possible solutions of theta p, they differ by 90 degrees. Here we have the sigma 1 appearing here, the sigma 2 must necessarily be appearing here, but that sigma 2 is nothing but sigma yy, and that is equal to 0. All this is fine, but how does it pertain to the connection with my shear stress? Well, I consider this one, the sigma 1. So, theta p and theta s differ by 45 degrees. This we have already seen. This fact was already written down bottom here, where we first obtained that twice theta p and twice theta s should differ by 90 degrees. And then we saw that theta p and theta s should differ by 45 degrees. Now, if that is so, where should we or how should we tilt this square such that we obtain the maximum possible value of the shear stress? So, we should definitely be going 45 degrees like this. Is this diagram complete? Yes or no? Well, if in a real classroom, I believe almost all of you would have said no, because we know that the planes on which the shear stresses are occurring are planes which are not, I repeat, which are not devoid of normal stresses, which means that I do have non-zero values of stresses appearing here also. Okay. Now, what is the physical meaning or physical manifestation of this 45 degree? Well, in most of these kinds of experiments, we use a metallic or a ductile material kind of bar, or a bar made of ductile material. Now, it has been experimentally found that these ductile materials, you will often find this statement made in textbooks that they fail in shear, that they are very prone to shear stresses. What this means is that whenever at those planes where you have the maximum value of the shear stresses, they are most susceptible to failure. Failure means it is very much possible that they lose their elasticity, that they go beyond their proportional limit, or perhaps they break altogether. Now, we have already found out that at an angle 45 degrees from this horizontal axis, we have the maximum possible value of the shear. If that is so, then this particular bar is very, very prone to failure to the horizontal axis. Now, if all of this is true, then should we not have a very dangerous situation occurring in this kind of a fashion. You see that I have tilted this line exactly like this. So, if I bring this kind of a tilted line here, it will look exactly like this. Now, we had already discussed in the previous chapter when we were discussing about material behavior that the ductile materials, they fail at such a surface that it looks like a cup and cone kind of fracture. So, if this is making an angle of 45 degrees, this gives us directly the indication that why that cup and cone kind of failure should be occurring, because you can imagine that if it really breaks apart, then it should look like from that side it should look like this, and from the bottom side it should look like this. So, ultimately it will be not like a perfect cup and cone, but roughly it will look like a cup and cone kind of fracture. Okay, so we do not have to discuss too much on that anymore, but this perhaps gives us a feel that all of these mathematical manipulations and rotation and all these things, it has some connections with practical engineering. Okay, going forward, what we would like to do is obtain some expressions, because till now it has been more or less a discussion about the angles and a very qualitative discussion about the shear stresses, the maximum shear stress and the principal stresses. What we would like to obtain very quickly is actual expressions for these principal stress values as well as the maximum shear stress values. So, what we can do? It's very easy. You see, we have already noted down a number of times earlier that at A and B we have the principal stress values. What is the value that we have at A? Well, you see, this is nothing but A is nothing but sigma average plus the radius, and B is nothing but sigma average minus the radius. And this in explicit form is nothing but sigma xx plus sigma yy by 2. This plus minus remains, and the r, if you remember, so I will borrow a little space from here. These are the two expressions. I am saying two because we have two possibilities here, plus or minus. So, these are the expressions of the principal stresses, and what do you think should be the expressions for the maximum shear stress? Well, we have already said that this is the D is where the maximum magnitude of the maximum shear stress is occurring. So, that is nothing but the radius, and this is also the radius. So, you please note that I have written this as sigma x dash and x dash, but I have also written here that principal stresses are traditionally represented by sigma 1 and sigma 2. So, I can very well write that this is sigma 1 comma sigma 2, because I am having two answers here. So, sigma 1 and sigma 2 will be correspondingly this. So, now expressions for the maximum shear stress, we come back to this discussion. So, tau max. You please note that just like we had we traditionally write our principal stresses like sigma 1 and sigma 2, so also we write our maximum shear stresses like tau max, and this you understand is nothing but plus and minus r. You also note that this plus and minus is only an offshoot of the choice of our mathematical machinery. In reality, what really matters is the value of this tau max, because as you have seen here in a real life example, that physical situation does not understand what our choice of plus and minus is. It only understands the particular value of the magnitude. Okay. So, inside a particular material there is no plus and minus. So, it understands particular values. So, but this is just, we understand this is a result of our mathematical machinery. Now, it is also very much possible to write this in terms of the sigma 1 and sigma 2. So, you understand here that this is sigma average, this is this R. So, you note quickly that we can write this very much as sigma 1 minus sigma 2 by 2. Okay. So, for example, what I am doing here is the plus 1 I am considering as 1 and the minus 1 I am considering as sigma 2. So, if I subtract sigma 1, if I do sigma 1 minus sigma 2, so I will be obtaining the R. So, this is what we have. Okay. Now, this is perhaps the right time to quickly do an example problem from our tutorial sheet. Okay. Okay. So, students who are viewing this live, you please note that I have picked up tutorial sheet number 8, which is the concept of stress and strain part 3. Okay. So, the problem that I am going to do is question number 8. So, so maybe I can finally erase this. If some people are live, can you, I would request the students to please answer in that live chat if they have access to this tutorial sheet right now. I am sure they can find it out later, but if they want to view it, I can tell them where to find it. So, if you can please answer, the technical people here can transmit that message to me. So, my question to the students is, do you all who are viewing here have access to the tutorial sheet number 8 right now or not? If you do not have, I will tell you how to access it. Okay. This problem does not have a very complicated diagram, so we can actually draw it quickly. So, we have a little stress element presented to us. So, this is again a square, and so let me first just copy down the information which is presented to us. You have the access, right? Okay, okay, thank you. So, so people who have access, maybe you can share them with your friends. So, if you still do not have access, I can tell you, I mean, this is not such a complicated problem. Whatever is there in the diagram, I have already drawn here. Okay, so, it is not such a big deal. Okay, so let me just read out the question. For the given state of stress, meaning whatever is presented in this diagram, determine, first of all, so there are different parts to this question. First of all, it has been asked to determine the orientation of the planes of the principal stresses. The principal stresses themselves is the second part of the question. The third part is asking us to find out the orientation of the plane of maximum in-plane shearing stress. The part D is asking us the maximum in-plane shearing stress, and part E is asking the corresponding normal stresses. So there's a lot of things going on. Let us pick them one by one, and that will also help to clarify a lot of concepts in the process. So first of all, the first order of business is to find out the orientation of the planes of the principal stresses. Okay, so basically what has been asked to us in the language of the discussion that we have been having is to find out the values of theta p. Okay, now this problem seems at first glance like a direct plug and play kind of problem, but we have to be a little bit careful here, especially because in the way that this diagram has been presented to us. You further note that in the tutorial sheet that has been circulated, perhaps you have access to that immediately, only in this tutorial sheet the answers are not given. Okay, so we will make them available to you. Okay, let us concentrate on this problem now. First of all, you note that this one is given, so perhaps it will be easier for us to discuss if we set up our coordinate axis. So we want to set up our coordinate axis like this in the usual fashion. Horizontal is x, vertical is y, no problem. Okay. Now this is given as 16 MPa. So sigma xx is very much 16 megapascals. Now this value is not given to us, but you see that the shear stress value is given to us, that is 60 MPa. Okay. So tau xy somehow it is given to us, but we have to be a little bit careful at this point. What is the carefulness all about? You see, in yesterday's discussion, we go back to our lectures, our lecture discussion, and I carve out a rough space here. Generally, when we were presenting our discussion, we set up our coordinate axis like this, and we said that following our positivity convention, this is our sigma xx, this is our tau xy, this is our tau xy, this is our sigma yy, and we will have the corresponding things on this side and this side. The most important thing to note is, by the positivity convention, this tau xy is vertically upward, but here the arrow has been given vertically downward. Correspondingly, and this is consistent here, you see that this is from left to right, but by the positivity convention, if I were to complete that picture, it would look like this. This would have been the correct positivity convention, generally speaking, without reference to any particular value. This would have been the whole thing. There is another problem here, that the sigma yy here is oriented opposite to what it should be by the positivity convention. So what we should be doing is to complete the presented information to us in a careful way in this fashion, that sigma xx is equal to 16 MPa, sigma yy is equal to minus 48 MPa, and tau xy is equal to this thing, the minus 60. I again emphasize that this has come out as negative, this has come out as negative, because the presented information to us has been oriented reverse to our chosen positivity convention. Okay. Now that we have those pieces of information in our hand, to find out theta p is just plug and play business. So all that we have to do for the part A of our problem is to use this formula this thing. You just put the values here. I don't have a calculator in my hand right now, but if you do it, you are going to obtain. So if you plug in the values, so what you are going to do as the next step, you are going to find some value, and then what you are going to do is you are going in your calculator, you are going to press tan inverse of that value. When you do a tan inverse of that value, it is going to give you one value. Now that one value, I believe that will be presented to you in the form of course, I'm skipping one step in between, that you will actually obtain the value of twice theta p. You will half that, you get minus 31, okay, 31 degrees. Now we all understand, we have already discussed this, that this is not the only solution. You also need a theta p plus 90 degrees. So which should be 59 degrees. So this and this together answers our first question, that determine the orientation of the planes of the principal stresses. Only one of them will not do. Okay. Next, for the second part, it has been asked, you find out the principal stresses. Well, this is quite easy. All that you have to do is just use these formulas. So this sigma 1 and sigma 2 values, we already have sigma xx, sigma yy and tau xy, which are listed out here. If you plug those values in, you will be able to obtain the part B answer. So after maybe doing this thing, we should have a bit more discussion about the physical interpretation of these answers. Like finding out the answers is one thing, like matching with the answers is one thing, but we should also appreciate the physical interpretation. So for the part B, what you will obtain is, so I am writing this as sigma max. So this comes out as 52 MPa. So this is only one of the answers, and this one, it corresponds to theta is equal to minus 31 degrees. So theta p is equal to minus 31 degrees. The other one is okay. The next question is the orientation of the plane of maximum in-plane shearing stress. So this also right now is just a plug and play kind of business. So all you have to do is utilize the formula. So maybe if I can just delete this thing. So for part C, what you will obtain is, one of the answers you will obtain as 14.04 degrees and the other one you will obtain as, again I am emphasizing that you really need to write down both these answers as part of your solution. Only one of them is not giving the correct orientation. Okay. So the maximum in-plane shearing stress. Now all this plug and play business is fine, but this is the right time for us to discuss something very, very important. So you please note that the part D of the question is asking us the maximum in-plane shearing stress. So what does that mean? Okay. So, from yesterday we have been discussing all along the reduced system which we have been referring to as the plane stress case. Now, in this plane stress we are looking from the top down and we are looking at a flat sheet like this, where the coordinate axes are oriented like x and y. But you also appreciate that there does very much exist this z direction, and we have mentioned that sigma zz is equal to 0, sigma zx is equal to 0 and sigma zy is equal to 0. So, this is the special case which we are referring to as plane stress. All of these problems pertain to that. Now, today when we obtained the principal stresses as well as the maximum values of the shear stresses, all of this was within this universe of plane stress business. But you note that suppose you tilt your orientation a little bit, or you just open your mind a little bit to the actual three-dimensionality of the situation. So, let us appreciate for a moment about the three-dimensionality of the situation. So, this particular discussion, let me remind you, it is not specific to this part D of the problem. So, I am restarting the lecture discussion here. So, this is the general discussion we are having, which will help us to solve this problem. So, in this general discussion we are going back to that point in yesterday's lecture where we set up a very special case of this three-dimensional situation, and we said that we would orient our x like this and our y like this, and definitely our z was like this. And from that point onwards we have been focusing by looking down on it, x and y. So, sigma xx, sigma y, all these things, and sigma z was all along 0. Now, when we found out the maximum shear stress, we found out its expression. After all these discussions, we found out the maximum values of the shear stress as sigma 1 minus sigma 2 by 2 plus minus. Okay. Now, all this thing was taking into consideration all the information that we have from the sigma xx, sigma yy and tau xy. But you note that in the direction which is perpendicular to the xy plane, that is in the z direction, there is no stress. So, suppose if we were to orient a two-dimensional stress element in the xz plane suppose, then would we not obtain something like this? Where you note this 0 is coming because nothing is really happening in the z direction, but this is very much a true result. Now, the problem is, you understand this tau max value is sigma 1 minus 0 by 2, and this tau max value is sigma 1 minus sigma 2 by 2. You consider only the plus value. Now, suppose it is true that both sigma 1 and sigma 2 are positive. Here also the sigma 1 will be positive consistently, which means that in the plane stress case where you have sigma 1 and sigma 2 to be positive, the value that you are obtaining for the so called maximum shear stress is not really the maximum shear stress, because this thing is certainly greater than this thing when sigma 1 and sigma 2 are positive. That means that this should really be referred to as the maximum shear stress, which is why in our question it has been asked very specifically that you find out the maximum in plane shear stress. So, it has implicit within that is you make your life easy, you stay within that plane, do not worry about the z axis business, and you consider the maximum value of the shear stress which you will obtain by taking this formula. That is what it means. Okay. So, what we really need to do as a result of all this discussion is that to answer our problem, all that you have to do is pick this value and be done with it. So, maybe we can number this as 1 and this is 2. So, You can find out this answer. Okay. And finally, for the part E, what has been asked is that find out the corresponding normal stress. Corresponding means when you have the maximum shear stress, what is the value of the corresponding normal stress. So, to again refer back to our circle, we have our circle like this. So, I am not drawing this circle with the values where I am respecting these values, rather I am just redrawing the diagram which I had drawn earlier, which I had kept for almost the entire lecture in this middle here. So, I had drawn this kind of a diagram where my horizontal axis was sigma x dash and this was my tau x dash y dash. Okay. This is the generic diagram. You understand that when I have the tau max here, and now in light of our newfound knowledge, I should really be referring to this as the maximum in plane shearing stress. So, when I have this thing, I have some non-zero value of the normal stresses. So, that is what has been asked here. So, all that you need to do is find out the sigma average here. Okay. So, okay. So, that you know, all that you have to do is find out sigma xx plus sigma yy by 2. Okay. Now, all this plug and play business is fine as I had mentioned earlier, but okay, okay. What is the doubt?
Whether theta s can be taken to be theta p minus 45 degrees instead of plus 45 degrees.
So, let me repeat the doubt because I noticed that whenever I have these discussions with the other professors, it is not audible to the audience. So, I believe if I understood correctly, the question is that if I can obtain the theta s by okay. So right. So theta p, instead of theta p plus 45, can I obtain theta p minus 45? So it's absolutely yes. So there is no problem here. So just to, I need a little bit of space. This is correct. Courtesy the fact that we have two possibilities of theta s, we have two possibilities of theta p. What I would suggest is you consider all these real values that we have obtained in this answer, you can check yourself. But some important information which I want to really highlight here is that this was our original stress element. This was the question which was given to us. Now, in the process of finding out the answer to question number A, where we discussed about the orientations of the principal stresses, and in part C, where we discussed about the orientation of the maximum shear stresses, it would perhaps make sense if we can actually have some kind of a visual representation, even if not that accurately, on this diagram itself. So, what are we actually talking about? So, whether we do it for part A of the problem or part C of the problem is absolutely equivalent. So, let us just consider this thing. So, you consider this, the theta s is equal to 14.04. Okay. What does it mean? It means that if I just delete all this thing to remove the clutter, you understand that this is parallel to the x axis. So, this theta s 14.04 degrees, it basically means that you need to tilt a line which is at 14.04 degrees here, and then draw a plane which is perpendicular to it, and then complete the square. This is quite easy to understand, but what is the meaning of this 104.04? Does it really mean that you go from here to another 104 degrees? Of course, you could do that, but can you perhaps extract the some interpretation from this diagram itself? You see what I have done here, the theta s plus 90 degrees. That theta s plus 90 degrees is very much present within this square itself. So, you see here, if this is theta s, then because this angle is 90 degrees, it means that that angle, this line that it makes with the horizontal, that is nothing but 14.04 plus 90 degree equal to 104.04 degree. So, this is the plane on which the other solution of the shear stress is going to appear, and it should make perfect sense, because if you have this kind of a shear stress here, you will definitely have a shear stress here also, and both of them will be equal in magnitude. So, just to complete the diagram, you should have like this, and again I want to emphasize, and this has direct connection with the part E of our problem. This diagram in itself is not complete, because you need to write the corresponding values of the normal stresses here, and that value will be given by the part E of the of our question. Yes. Okay. So, Professor Gautam Chakraborty is sitting here, and he has very kindly and very nicely mentioned that so all of this is fine where we are directly using our nice expressions, but what we can do as an alternative is for our tau max, we can go back to the beginning. We can go back to our equation number 4 from yesterday, and we can see like this. Now, you see, because we have already solved part C of the problem, where we found out the maximum orientations or the orientation of the planes where the maximum shear stress would be occurring. So, we have two explicit values available in our hand. So, if we just come here and substitute theta equal to theta s once and theta is equal to theta is the other value 104.04 degrees again, what we should be obtaining is the value of this maximum shear stress. In fact, we would be obtaining the values of the maximum in plane shearing stresses with the correct sign and everything, and that should be absolutely clear to us. Sorry? Okay. So, I have not given any values to the students. So. Right. So what Professor Samantara here is mentioning is that as a result of this, suppose you use one particular value of theta s and it comes out to be, so as a result of a particular substitution, when you substitute theta equal to theta s and it gives a negative value of tau x dash y dash, then you really have to understand that in your diagram, you should be representing that answer not like this. So, this would be wrong because that is a negative value. This respects the positivity convention. So, you should really be writing this like this, and of course that would be with the positive magnitude. Okay. So I would encourage all the students who viewed it to maybe post their doubts in that live chat, and after the end of this lecture I can go there into the YouTube link. It will be always archived. I can answer some of the questions from there.
Question from someone.
Okay.
It says, how can you tell that 52 MPa corresponds to minus 31 degree and the other answer minus 84 MPa is for 59 degree?
Okay, so basically when I found out these answers, I actually used my calculator. So you also have to do this. So you go, in the part A of our problem, we found out two answers for minus 31 and plus 59. What you will do is you go and find out you use the expression of sigma x dash, you put theta equal to minus 31, one answer you will get. You put 59 degrees, you will get another answer. That's it. No, it is not by magic that I am writing this. Okay, so I actually use my calculator to find out these things.
You can tell this is 1 because it varies.
Yes.
Okay, so can you announce that we are going to have class tomorrow also?
Tomorrow?
Yes, we will have to go on class tomorrow so that we are ready. We have a slot.
Okay. So because of these special circumstances, what we have arranged here is that, and our mechanics coordinator, the overall coordinator of our mechanics course is very much present here, Professor Samanta Rai, and he has notified us that tomorrow also from 4 to 6 there will be a mechanics class. So this special arrangement will help us, that will ensure that all the sections are now on the same page from the next week. Okay, thank you. Thank you very much.